Welcome to our Day 3 notes for Unit 8 of Advanced Chemistry. Today we're going to be going over limiting reactant calculations. Sometimes these are called limiting reagent problems, and it is just like our previous couple of days in this unit going to involve some math and some dimensional analysis. So what a limiting reactant calculation is going to do is it's going to ask us to consider the amounts of two reactants, and we're going to try and figure out how much product we can make with that amount of reactants. So to kind of illustrate this with a more relatable example before we jump into some stoichiometry, we are going to look at a cookie recipe to talk a little bit about limiting reactants versus excess reactants, which are terms you will see today as we work through our problems. Okay, so right here we have a cookie recipe, and we are trying to make cookies, but we do not want to leave our home, okay? And so what we're going to do is we're going to look at our cookie recipe, and we're going to look at what we find at our home, and we're going to try and see just how many cookies can I make without leaving my house, okay? And so right here I have this many eggs, 6 eggs, and I'm going to come look at my recipe, and I see that to make one batch of cookies, I need 4 eggs, okay? I'm told that I can make half batches, so if I have 6 eggs at home, and I need to make a batch of cookies with 4 eggs, I can actually make 1.5 batches from those 6 eggs, okay? And if you're thinking a little bit like this might look like a dimensional analysis problem, then you are correct, because we could actually set this up a different way. We could say I have 6 eggs, that would be my given, and then I can look at my recipe, and I see that I need 4 eggs to make one batch of cookies, and if I solved that out, that simple one-step dimensional analysis problem, I would get 1.5, which is how many batches we have over here. So we are going to be, as we consider our products that we make today in our chemical equations, and using our chemical equations, we're going to be using dimensional analysis. But right now, while we are illustrating this example, we're just going to kind of do some math in our head, because this is just a simple one-step problem. So with 5 cups of flour, if I am using 2 cups for each batch, I can actually make 2.5 batches of cookies. With 4.5 cups of sugar, 1.5 cups per batch, I could make 3 batches of cookies if we're just thinking about our sugar. And with our 4 sticks of butter, since we need 2 sticks for each batch, I could potentially make 2 batches from 4 sticks. So what we're going to do is we're going to look at all these batches over here, and I see that the lowest number is 1.5, okay? So because I only have 6 eggs, if I am staying true to my recipe, I can only make a batch and a half of cookies, okay? So this is what is going to limit my cookie baking today, is the fact that I only have 6 eggs, okay? Because I need 4 eggs to make one batch. That is not going to change. They're not going to be good cookies if I don't have my 4 eggs in there. So the eggs are what we call a limiting reactant, okay? So the eggs are going to be used up first, because if we make our full 1.5 batches, we will use all 6 eggs. So the limiting reactant in a chemistry problem and in this baking example is what we used up first. That is our eggs. The excess reactants are going to be everything else that was left over. So I'm going to write left over right here, okay? So everything else that we didn't end up using up because we ran out of eggs, and so it didn't make sense to just keep making cookies without our eggs, okay? So here, my excess reactants are flour, sugar, and butter, okay? And for my butter, we're asked here, how much are we going to actually end up using to make our cookies? We had 4 sticks, but we're not going to use all 4 sticks because we can only make 1.5 batches. So if we are going to make 1.5 batches of cookies, 1.5 batches worth of butter is just going to be 3 sticks. So we'll just need 3 sticks of butter for a batch and a half, and that means that we'll actually have 1 stick of butter left over at the end. So that's why it's an excess reactant. We have some left over, okay? For the eggs, it's our limiting reactant because, again, we used it all up, okay? We are going to use all 6 eggs to make our batch and a half, and so that means we're going to have 0 eggs left over. So again, a limiting versus an excess reactant. Very important concept that we need to keep in mind today. This last question right here is a percent yield question. We're asked what the percent yield is if we normally are able to make a batch of 55 cookies. However, while we were cooking, we ate some dough, we also burnt some cookies, and so we only ended up making 48 cookies. And just go ahead and make those changes here. There was a typo on our notes this time. Okay. If you go on to calculate your percent yield, we learned how to do this last class, but just as a reminder, percent yield is the experimental amount over the theoretical amount multiplied by 100 to give us a percentage. And that formula is on your periodic table and formula sheet. You do not have to memorize that. Always available for you right there. And if you went ahead and did that math, which you should just to practice and make sure you can type things into your calculator correctly, you should get 87% of 0% yield. So pretty good. Okay. So now that we've kind of gone over some basics about what a limiting reactant and excess reactant are, we're going to get more into the chemistry of it, okay? So this might have been like a little bit of a silly example, but this is exactly the process that we are going to use when we solve a limiting reactant or limiting reagent problem. The only change is that our recipe is going to be our chemical reaction. So we're going to consider our chemical reaction our recipe here, and you can get wise to the fact that you do have a limiting reactant problem because the problem itself will give you starting amounts of both reactants, and then you need to find the amount of product you can produce from those two reactants. So up until this point, we have told you, we gave you this amount of a reactant, and you were told that you had an excess amount of the other reactant to react with it. That is no longer the case. If you have one of these problems, if you have a limiting reactant problem, you are going to be given the starting amounts of both reactants, and you're going to have to figure out which one runs out first, because that's going to be the one that you're going to use to figure out how much product you make. Okay? So that's what we're going to do. We're going to find how much product we could theoretically make. That's called our theoretical yield. And what you're going to do there is you're going to take both of your reactants, and you're going to find out how much product they can produce. So you're going to set up 2-dimensional analysis problems, and whichever product amount is the smallest is the maximum amount of product you can make. Okay? Whichever one runs out first. To figure out which one is the limiting reactant, you are going to see which reactant made the least amount of product. The reactant that made the least amount of product is your limiting reactant. It's going to run out first. The other reactant is in excess. Okay? To figure out the amount of limiting reactant left over, because you will often be asked to do this, to figure out the amount of limiting reactant left over, this is very easy. It will always be none. Your limiting reactant will be fully used up. You can say none will be left over. And then finally, to figure out the amount of the other reactant used, or the amount of the other product produced, you can use the amount of the limiting reactant to perform a stoichiometry calculation to find the amount of the other substance you used or produced. Okay? So with this kind of background information for you to refer back to, we're going to actually go through a problem and work one together so you can see how we do this with stoichiometry without a simple baking recipe. It's going to get a little bit more complicated. So flip over to page 10, example 14. You are told here that you have 35.60 grams of zinc and you're reacting that with 100 grams of iron 3 sulfate. So right here, right off the bat, we are given two amounts of our reactants, so we're going to have to figure out which one is the limiting reactant. And what is the theoretical or maximum yield of pure iron in grams? So first things first, just like our previous problems, we will write out a balanced reaction. Okay, step one, write a balanced reaction. So I have zinc here. It's going to react with iron 3 sulfate, so Fe2SO4 with a 3 subscript. Make sure you put that sulfate in parentheses. And this looks like a basic single replacement reaction. We are going to assume all reactions in this unit go through. So zinc is going to kick iron out of that spot. And of course, iron here has that +3 charge, sulfate with that -2 charge, and zinc as an ion will have a +2 charge. So our zinc and our sulfate will cancel each other out here. And then iron's going to go be by itself. Okay? You're going to balance that as well. Having a balanced reaction is important, so that way your coefficients will be correct when you set up a mole ratio. And then we're going to set up a stoichiometry map, okay? We are trying to find out how much pure iron we can make in grams. So I'm going to write underneath my iron, grams. We need to know how many grams of iron can we make. I'm going to write my other amounts over under my other reactants. So I have 35.60 grams of zinc, and I have 100.00 grams of iron 3 sulfate. And so I'm going to make myself a stoichiometry map here, okay? If I need to get from grams of these reactants here to grams of iron, I will write myself out a stoichiometry map. So I can go from grams to moles with my molar mass conversion. I can create a mole bridge by using a mole ratio. Now I'm in moles of iron. I can use molar mass to get from moles to grams here. Okay? Same thing here. If I want to get from grams of iron 3 sulfate to grams of iron, I'm going to go from grams to moles of this. Same thing, molar mass. And then I can go use a mole ratio to get from moles of this to moles of iron. Okay? And then once we're in moles of iron, we already know that in order to get to grams of iron, we're going to have to go from moles to grams with molar mass. Okay, so these are my two maps. So one of the things you're going to notice right off the bat that's different about some of our previous problems is that you are going to have to set up two different dimensional analysis problems here. Okay, you're going to have to set up one that starts with the given 35.60 grams of zinc, and you're going to have to set up another one starts with 100 grams of iron 3 sulfate. Okay? So that's what we're going to do. Using our stoich maps, we see that we have two 3-step problems to set up. Okay? And so I'm just going to set these up using my stoichiometry map. This is nothing new that you have been exposed to before. You have definitely done this. So just use that stoichiometry map to set up your dimensional analysis here. Okay? So my molar mass of zinc is 65.39 grams per mole. Can set up my mole ratio. Go from moles of zinc to moles of iron. For every 3 moles of zinc, we can make 2 moles of iron. And then we're going to go from moles of iron to grams of iron. So for every 1 mole of iron, we have 55.85 grams. So we're going to solve that here in a sec. I'm going to set up this other one though first. So in iron 3 sulfate, if you calculate that molar mass, you will see that there are 399.88 grams of iron sulfate in 1 mole of iron sulfate. Apologies, it's a little cramped in here. I will draw a little bit bigger parentheses over here. Okay, Then over here, I've got my moles of iron 3 sulfate. And we're going to go to moles of iron, just like our map tells us that we drew to help keep ourselves organized. So for every 1 mole of iron 3 sulfate, we can make 2 moles of iron. And then in 1 mole of iron, we have 55.85 grams of iron. Okay. Again, just use your periodic table to pull your average atomic masses like that for iron. If you need to calculate something like iron 3 sulfate and you need to show your work off to the side, that's a good idea. Do what you need to do to be successful. But there are our dimensional analysis problems set up. So if you put these in your calculator, I'll do this under the dot cam so y'all can see, we can figure out how much we could potentially produce from this amount of each of our reactants. So first up, do 35.60 grams of zinc times 2 moles times 55.85. Close that parenthesis. Divide it by everything on the bottom, 65.39 times 3. Oops, and I forgot to include a parenthesis over here. That would have been bad. 65.39 times 3. Close my parenthesis. Then hit enter. And I should get this 20.27. Okay? So I had 4 sig figs in my given. I'm going to go ahead and put 20.27 grams of iron. That's what unit we are left with. Okay? So if we have this much zinc, theoretically we can produce this much iron. But we are not done yet. We have to go see how much iron we could theoretically produce from this amount of iron 3 sulfate. Okay? We have to compare them to see which one's going to run out first. Okay? So again, type this into our calculator, multiply everything on the top, 100 times 2 times 55.85, close my parentheses, divide by 399.88, and that is it on the bottom. Okay, we should get 27.933 because we can go for 5 sig figs here. So 27.933 grams of iron. Okay? So, again, if we look back to our page, our previous page, figuring out our limiting reactant, to figure out which one is the limiting reactant, we're going to see which reactant made the least amount of product. This is our limiting reactant. This is what's going to run out first. Okay? So over here, I see that the least amount of product made came out of this dimensional analysis problem that I just solved. Okay? 20.27 grams is less than 27.933 grams. Okay? So I'm going to go back and see this one, look back to the beginning, and see what reactant made that amount of iron. So the reactant in question is zinc here, okay? So zinc is our limiting reactant, okay? Zinc is our limiting reactant. If you want to highlight it down here so you see where you're getting that from. Zinc, because we were only able to make 20.27 grams of iron using zinc. We were only able to make 20.27 grams of iron using zinc. We are going to run out of zinc first before we run out of iron 3 sulfate. Okay? So because this was our limiting reactant, our other reactant is our excess. Okay? Our excess, the one that is left over, remember? So this is the one that made more product, potentially. This is not going to get made. We're not going to make 27.933 because we run out of zinc before then. We run out at 20.27 grams of iron. So our excess reactant is iron 3 sulfate. And in order to figure out how many grams of it will be used, we're going to do a little bit of a reverse dimensional analysis from what we had over here, okay? So we want to know how many grams of iron 3 sulfate is used? We can do that by taking the product we made using our limiting reactant here and starting that off in our problem as our given, okay? So what we're going to do is we're going to take our 20.27 grams of iron and we're going to work backwards, because 20.27 grams of iron is all we are able to make when we have these amounts of reactants. And so what we're going to do is we're going to work backwards. We're going to try and figure out from 20.27 grams of iron, how many grams did I use up of my iron 3 sulfate in the process of making that 20.27 grams of iron. Okay? So we're going to go backwards. We're going to go grams of iron to moles of iron to moles of iron 3 sulfate to grams of iron 3 sulfate to figure out just how many grams of iron 3 sulfate were used, again, to make this 20.27 grams of iron. So here we go. We know there are 55.85 grams of iron in 1 mole of iron. Next up, we're going to go mole to mole. Moles of iron to moles of iron 2 sulfate, or iron 3 sulfate, apologies. So we know, for every 2 moles of iron, we had to put in 1 mole of iron 3 sulfate. Okay? And then last but not least, getting a little cramped down here, 1 mole of iron 3 sulfate is equal to 399.88 grams of our iron 3 sulfate. So there's our dimensional analysis here. So we can figure out, my lights are going off. And we're back. Okay. So now that we've set this up, we can calculate how many grams of iron 3 sulfate we should have used to make this 20.27 grams of iron. And if you put that into your calculator here, you get 20.27 times 399.88, divide that by 2 times 55.85, you should get 72.57 for sig figs, 72.57 grams of this compound here. Okay? So this is how many grams will be used. So this is how many grams will be used. Okay? How many grams of our excess reactant will be used? Our next question asks us how much of the excess reactant will be left over. How much is left over at the end of the experiment? All we have to do to figure out how much was left over, y'all, is just take our 100 grams here, the amount that we started with, and we're going to subtract what we used from what we started with. Okay? So we used 72.57 grams. That's what we just solved for. This is what we used. And when we solve for that, we should get 27.43 grams of that compound. So this is what was left over. This was our excess. Okay. Next up, letter E. What is the identity of the other product? Well, we can go right back up here to our equation and see. So we've been talking a lot about iron as our product. The identity of our other product is zinc sulfate. Okay, we have zinc sulfate here. So the identity of our other product is zinc sulfate. And then here we're asked how many grams of it could be theoretically produced. how many grams could be theoretically produced? Okay? Again, this is going to be a similar process to what we were doing before. We already figured out that the reactant that's going to be limiting here in our problem is zinc, because zinc ran out first when we compared to our iron 3 sulfate. So if we want to figure out how much zinc sulfate we can make, we can simply get our limiting reactant, our 35.60 grams of zinc. We're going to start with the limiting. If you start with your limiting reactant, you can set up dimensional analysis to solve for your amount of your other product. Okay? So here I'm going to solve, instead of going to moles of iron and then grams of iron, I'm going to go from zinc to moles of zinc sulfate and then grams of zinc sulfate. Okay? So I'm going to take those steps. I'm going to go from grams of zinc to moles of zinc, and then we're going to go from moles of zinc to moles of zinc sulfate, and then finally we're going to go from moles of zinc sulfate to grams of zinc sulfate. Okay? And so I'm going to solve for that. So we're going to fill in our little numbers here. I know that there are 65.39 grams of zinc and 1 mole of zinc. Again, you just look at your periodic table to figure that out. And I know, based on my reaction I wrote up here, that for every 3 moles of zinc, we can make 3 moles of zinc sulfate. So my mole ratio is going to be 3 to 3. And then my molar mass of zinc sulfate, if I come over to my periodic table and I find my average atomic masses of zinc and sulfur and oxygen and take into account my subscripts, I find that for every 1 mole of zinc, we have 161.45 grams of zinc. So we can type this into our calculator as well. 35.6 times 3 times 161.45. Then we're going to divide by 65.39 times 3, which really, these kind of cancel each other out. And we'll get 87.897. So if we want to round this to 4 sig figs, and think about that in your head real quick. If you rounded it to 87.90, then you were correct. 87.90 grams of zinc sulfate is what we could theoretically produce, taking into account our limiting reactant. Okay? So we've answered both parts of that question. Letter F says to list off all substances and amounts theoretically left in the container at the end of the reaction. So what is left in the container at the end of the reaction? We actually don't have to do any more calculations here. We already found it all out. Okay? So the only things that are going to be left are going to be, of course, our products. We're going to make some zinc sulfate. We're going to make some iron, which we calculated how much we were going to make of each. The other thing that's going to be left is the leftover iron 3 sulfate that we did not use. Okay? So we didn't use up all of this. We used up all of our zinc, but we had some of this left over, and we already calculated that. So we're going to have 87.90 grams of zinc sulfate, because we just calculated that's how much zinc sulfate product we're going to make. We're going to have 20.27 grams of iron, because again, up here we figured out that with that amount of zinc, we could make this much iron. And then last but not least, we're going to have our leftover iron 3 sulfate. So we said we had 27.43 grams left over of this. So this is everything that is left in our reaction container at the end of our reaction. We have no zinc left over, because it was all used up. No zinc left over because it was all used up. And then last but not least, we have letter G. It asks us to figure out the percent yield of the reaction. We were told that we made 19.64 grams of pure iron in the lab. So that's our experimental value. And so if we set up our percent yield equation, go ahead and pause me and set that up. You should already know how to do that. If you're back, there's the equation that you can grab from your formula chart. If you plug in your numbers, hopefully you were able to go grab your numbers. We made 19.64 grams of iron experimentally in the lab. And we said that theoretically, with our amount of zinc, we should be able to make 20.27 grams. So that is our theoretical. Multiply that by 100. You should get 96.89%. That's a pretty darn good percent yield. So that was a lot. There are a lot of steps to some of these limiting reactant problems. But again, figure out what your question is asking you. Take it step by step, okay? As in any problem, you're always going to have to do, if you have a limiting reactant problem, you're going to have to do two-dimensional analysis problems. You're going to have to set up two of these, one for each of your reactants. So make sure you're setting up both so you can compare, and so that way you can get all your points there. Okay? And then as you go through, just make sure you are answering the question that it is asking. You should be able to tackle these problems. With anything, like with anything in this class, practice makes perfect, so there's a lot on your practice worksheet for you to do. But before you tackle that practice worksheet, go ahead and flip over to example 15. I want you to try example 15 by yourself. Okay? I recommend that you pause me here so that way you can try example 15. There's going to be a little bit of molar volume involved here, so some different conversions that you're going to have to refresh your memory on perhaps. But I want you to try this one, and then once you've tried it, unpause and come back and check your work. Okay, if you unpause me, then you should now be able to check your work. So up top with A, we have our two setups. We were able to determine that our nitrogen was our limiting reactant. We're going to run out of nitrogen first. We were able to make less of the product with the available nitrogen. So it's going to run out first. And so we can identify that limiting and that excess here. I'm going to slowly start moving up. We're then asked how much hydrogen will be used in the reaction. So our hydrogen here is our excess. And so we can calculate going backwards using our 15 grams of nitrogen. We can go ahead and figure out how much hydrogen we're going to use. Okay? So just go ahead and use your nitrogen, to figure out how much hydrogen is going to react with that nitrogen to make you this 24 liters of ammonia. You can figure out how much you have left over. And right here, we have our nitrogen. We're going to use all of it. None will be left over. And then we can figure out how much we have left in our container at the end of our reaction. And then our percent yield. So over here, I just realized that I did something a little bit different on this problem figuring out how much of our other reactant we used than I did on the previous page. So right here, I started off using my given nitrogen. And over on the other side, I started off using the final product amount, okay? What I mean by that is over here, I started with my final product amount. The other way that we typically have y'all do this, if you go back over to letter C on example 14, is we will have y'all start with the amount of your limiting reactant, okay? So to find out the amount used over here, you can do 35.60 grams of zinc, and then you can convert to your moles of zinc, and then you can convert to your moles of your iron 3 sulfate, and then you can convert to your grams of iron 3 sulfate. Okay. So that's how you will typically go about doing that. You could do it this other way, but again, I'd recommend you do it this way instead, because you will get that. You'll start out with that given, and you won't have any issues with your final answer having rounded your product up here. Okay. But you should get still around 72.57 grams here. Just a different way to approach the problem. Okay. So hopefully that was beneficial. And if you need to go back and rewind because I went through the previous answers through example 15 too fast, if you need to pause me to go ahead and see some of the work that I laid out here, go ahead and do that. If you have any further questions, you can ask me or one of the other chem teachers for help. We'll be happy to elaborate. Okay, thank you.